Hello. I want to review the first two online homework assignments that you've already turned in and have been graded. Just so, in case you haven't seen the comments that I put on Canvas, I'll quickly go through the questions and answers for all the online homework and quizzes that we're going to do this for the rest of the semester. So this is number 5, dealing with thermodynamics and kinetics. First question was, what's the difference between heat and temperature? I was just looking for heat being a measurement of the movement of atoms and molecules. It's a transfer of energy. I was looking for something that involved movement of things around or transfer of energy. Temperature is a measure of the amount of heat energy in an object, but it's not the same as energy. Number 2 was asking, give an example of each of the types of energy. There's thousands of possible answers. Sound could be music coming out of speakers. Chemical could be energy released when fuel burns, or a lot of people said batteries, which is fine. Electrical energy, lightning bolt, energy stored or released from a battery. Light energy, sunlight, lasers, ultraviolet light even would be okay, or infrared radiation is fine. Heat from just heat energy, fireplace, many things. Most people got all those right. This question here, what I was looking for was calculate the energy of the enthalpy change of a reaction using bond energies. So I think my camera's getting that. Yep, this is the combustion of propane, C3H8, plus 5 moles of oxygen gives you 3 moles of CO2 and 4 moles of water. Here's the bond energies that you were given in kilocalories per mole. What I was looking for was if you would draw out the reaction like so. Here's propane, here's your 5 molecules of oxygen to give you 3 molecules of CO2 and 4 molecules of water. And so in this molecule you have 2 carbon-carbon single bonds with this total energy. You have 1, 2, 3, 4, 5, 6, 7, 8 carbon-hydrogen bonds. That's this sum here. And you have 5 oxygen-oxygen double bonds. Here's this energy. That's the amount of energy you have to put in to break the bonds. And then you get back, subtract 1, 2 of these bonds in CO2, but there's 3 of them, so 6 times the bond energy of a carbon-oxygen double bond, plus 8 oxygen-hydrogen bond energies, which is here. You add that up. So you'd have 1,553 kcals minus 1964, so it came out to be a negative 411 kilocalories, which is an exothermic reaction. And you probably already remember or know that anytime you burn something, fuel, you always get an exothermic reaction. Heat is released. Number 4 was asking about just types of energy, transfers of energy. Gasoline consists of a mixture of compounds with the formula C8H18. Considering the energy released in the above reaction, how a mechanical device like a car works, is all of this energy of the fuel available to move the car? Explain why or why not. Where is the energy lost? Well, most of you got this right. I was looking for things like losing energy to friction between the tires and the road, air resistance, energy lost running the car itself, the air conditioning, the radio, the fans, energy lost as heating up the engine, or using in the inefficiency of the engine itself, there's a lot of energy lost. So everybody did well on that one, I believe. And then number 5 on this assignment asked a similar sort of question. Describe the energy conversions taking place when a roller coaster operates. What are all the types of energy involved? How is some of the energy lost or wasted during the ride? What I was looking for here was something about mechanical energy being the energy needed to pull the train up to the top of the hill to generate a lot of potential energy. And then that potential energy is converted into kinetic energy of the moving train. Energy is lost as sound, friction between the wheels and the track itself. Energy is lost as friction between air resistance or drag. And that's pretty much it for that question. Number 6 asked just a bunch of different processes. Could you identify if it was exothermic, meaning heat was given off, or endothermic, heat was consumed? So a process that absorbs heat from the surroundings is endothermic. A process that releases heat is exothermic. A reaction with a negative delta H is the same, exothermic, giving up energy or giving off heat. Melting a solid takes energy, so that's endothermic. You have to heat it up. Freezing a liquid is the opposite of melting, so that's exothermic. Boiling water, you have to put energy in, like on a stove, so that's endothermic. And photosynthesis is also endothermic. You have to use sunlight to cause the reaction to occur. Number 7 was, how is the temperature of an object related to the kinetic energy of the atoms or molecules it contains? I was looking for something about temperature increasing, things moving faster, or temperature decreasing, atoms and molecules moving slower, and therefore if they move faster they have higher energy. Kinetic energy moves up. If they move slower, the kinetic energy goes down. Number 8 was asking about entropy, the disorder of things, reactions, processes, whatever. So I think everybody pretty much got all these, but I'll still go through them. Cleaning your house means going from disorder to order, so that's entropy decreasing. Burning wood is forming a lot of CO2 and water as gas, so that's a disordered system. Entropy's increasing. Steam condensing to a window is gas going to liquid, so disorder to order, that's a decrease in entropy. Atmospheric CO2 dissolving in the ocean. Atmospheric CO2 is a gas, dissolving in the ocean is a liquid, so to speak, or an aqueous solution. So ions dissolve, or CO2 dissolved in the ocean is more ordered, so entropy decreases. Perfume vapors diffusing throughout a room, that's an increase in entropy because the vapors are spreading around the room in countless directions. The combustion of gasoline in an engine is, again, increasing entropy because you're forming lots of CO2 and water as gases from an ordered fuel, so that's an increase. Plants using photosynthesis to produce oxygen is a decrease in entropy because you're taking 6 CO2 molecules and 6 water molecules to make 1 glucose molecule and releasing 6 oxygens. So you're going from a very disordered to an ordered system, so there's a decrease in entropy for that process. Number 9 was briefly explain what is meant by a spontaneous reaction or process. How is the sign of delta G, free energy, related to the spontaneity? I was looking for you saying something about this delta G being negative if it's spontaneous. And spontaneous means that it's a process that once you get it started, it continues on its own without outside influence. That just means that until the limiting reactant runs out, the reaction will just keep on going. But you do have to give it a certain amount of energy to get it started. That's what this hill is. You have to have a kickstart, light it with a match or heat it up or stir it. That you need an activation energy, even though it's spontaneous. Number 10 was asking you about could you recognize a general picture of energy changes as being spontaneous or not, or fast or slow. So this one here, which one of these is a slow reaction with a large positive free energy change? That would be this one. It's a positive free energy change and it's slow because the hill from left to right is rather large. A slow reaction with a large negative free energy change is A. It has a large hill, but it has a negative free energy change, and it's relatively large, so that's A. A fast reaction with a small positive free energy change. So you're looking for something that has a small hill, like this, or one of these two most likely, and it has a positive energy change, so that would be only this one, D. Fast reaction with a large negative free energy change would then be this one because it still has a small activation energy, so it's fast, and it has a large negative free energy change. This is a negative change, this is a positive change on an energy diagram. Okay, well, list 3 ways you can increase the rate or speed of a reaction: raise temperature, increase the reactant concentration, or use a catalyst. 12, what's the activation energy of a reaction? That's this hill. It's the difference in energy between the reactants and the highest energy. It's the amount of energy necessary for reactants to overcome the energy barrier to reaction. So once the reactants get up to the top of the hill, they can then move on to products or go back to the starting material. Does a slow chemical reaction have a large or small activation energy? It has a large hill, a large energy barrier. Number 13, how does a catalyst affect the rate or speed of a reaction? It just lowers the activation energy. It lowers the hill that the reactants have to climb. Therefore, it speeds up the reaction. If the hill is small, so this would be a slow reaction, this would be a fast reaction. The catalyst would change it from something like this to something like this, so it would be sped up. It provides a different pathway so that it speeds things up. Give two examples of a catalyst in action: enzymes breaking down food, a catalytic converter in a car exhaust. A lot of you looked up things on the internet and found some interesting examples of metal compounds being used as catalysts in all sorts of chemical reactions. So everybody seems to do pretty well on that one as well. Now the one that I just graded, that was homework number 5. Homework number 6, the one I just graded, dealt with equilibrium and gases. So number 1 here is it says answer the following questions. Which part of the graph reflects equilibrium? Well, when you have rate versus time, then the point at which the rate has become constant for both reverse and forward reaction, that's equilibrium. From this point on is equilibrium. Anything before the rates are equal is not an equilibrium state. So anything from here to here is not an equilibrium. I was just looking for you to be close in that respect. This question was dealing with writing equilibrium constants and Le Chatelier's principle. You have this reaction here. It's got a somewhat large but not huge KEQ. The equilibrium constant is, keep in mind that if there's a solid in a reaction, it does not occur in an equilibrium expression. Solids and pure liquids do not occur in these K expressions because their concentrations don't change. The concentration of a solid and a liquid is a constant. The only things that change concentrations are gases and aqueous solutions. So therefore, this K would just be the concentration of CO2 to the third power divided by the concentration of carbon monoxide to the third power. Those are the gases. The Fe2O3 and the iron are not part of it. According to the size here of KEQ, does this favor reactants or products? Well, it's larger than 1, so it favors products. If it's less than 1, it favors reactants. If it's equal to 1, they're about equal. Doesn't favor either side. Give one way to shift the equilibrium to the left. You could do many things. I said here add CO2, it's going to shift it left. Remove carbon monoxide, it's going to shift it left. You could, what else could you do? Well, if you knew if it was endothermic or exothermic, you could raise the temperature or lower the temperature, but I didn't tell you anything about that, so you couldn't really say anything about temperature in this case. Adding iron or removing this or removing that or adding that wouldn't affect the equilibrium, so you had to say something about the gases changing. Same sort of problem here, number 3. Nitric oxide is synthesized from nitrogen and oxygen gas, plus it's endothermic, so you have to add in heat. So nitrogen and oxygen are the main components of air. This is toxic gas. The equilibrium expression for this, they're all gases, so they are all included. It would be the products over the reactants, so K equals the concentration of NO to the second power. The coefficients become the power. Divided by the reactants, so N2 and O2 both have a 1 in front of them, so they're raised to the first power. We don't need to write it. Do you think K is a very large number or a very small number? Well, we know these are very stable, and that's not toxic. So this is the air. If this reaction happened to any great extent, we wouldn't be around. There'd be too much NO in the air to breathe. So we know this reaction is not likely to occur. It's a very slow reaction. So the K for this reaction is very small, much less than 1. And it's because of what I just said. These are very stable. So the reaction lies far to the left. Give 2 ways to shift the equilibrium to the left. I said add N2. To the right. Add N2, it'll shift to the right. Add oxygen, it'll shift to the right. Or you could remove NO. sorry, that's out of view. You could add N2, it shifts to the right. Add oxygen, it shifts to the right. Remove NO gas, it'll shift to the right. You could raise the temperature, it'll shift to the right. How do you shift it to the left? You could add product, it'll shift to the left. You could remove either of the reactants, or you could lower the temperature. All those things will shift it to the left. The next page was here. It says analyze these Ka values in this table and answer some questions. So yeah, you can see it's listed from large Ka to small. That's a relative scale. Those are still numbers that are less than 1, but these are all weak acids. It just says that what the table means is this number being at the top, being the largest value, means that phosphoric acid is the most acidic of all these given. Hydrosulfuric acid at the bottom with the smallest Ka is the least acidic. Where would sulfuric acid be placed? Well, I was hoping you'd remember that that's a very strong acid, so it's the K of that acid is much, much larger than 1. We don't even express K. It's just much larger than 1. We don't care. So it would be larger than any of these, so it would be at the top of the table. Briefly summarize some characteristics unique to the three states of matter. This is sort of what I was looking for. Most people got all these right. Some you might have been a little repetitive in your answer, so I didn't give you full credit, but solids retain their shape and volume. They don't flow. They can't be compressed. Liquids assume the shape of the container. They flow more easily, and they cannot be compressed like solids. Gases completely fill their container, so they assume the shape and the volume of their container. They flow easily, and they can be compressed. Define pressure in 3 common units for pressure. Pressure is a force. I was looking for force per area. Many, many units, but the common ones are atmospheres, millimeters of mercury, which is the same as a torr, pascals, or pounds per square inch. A helium weather balloon expands as it rises in the air because the atmospheric pressure drops. That's Boyle's law. Pressure and volume are inversely proportional. As one goes up, the other one goes down. Atmospheric pressure on the top of Mount Whitney is about 440 millimeters of mercury, so that's much less than atmospheric pressure. How many atmospheres are this? I wanted to see something like this, where you divide that by the definition of an atmosphere being 760 millimeters of mercury, so it's a little more than half an atmosphere. 0.579 atmospheres, or since this only has 2 sig figs, 0.58 atmospheres would be the correct answer as well. Why does water boil at less than 100 degrees on top of this peak? Because there's just less air pressure. There's less air pushing down on the water, lower atmospheric pressure, so less energy is needed to for the air bubbles, the water vapor to get out. Right. Third page here is part of that question. This is a third part of that question. It says, if a helium-filled balloon floated to the top of this mountain from sea level, where its volume was 2 liters and the pressure was 750, what's its volume going to be? Again, that's Boyle's law. So you take the initial pressure times the initial volume, right here, and divide it by the new pressure, the lower pressure. That's a number greater than 1 times the initial volume. Therefore, the final volume is going to be more than 2. It's going to expand, as we know. The balloon will expand as it goes higher in the air, just like a hot air balloon expands as it rises into the upper atmosphere. When liquid nitrogen is poured over a balloon with air, the balloon's volume decreases greatly. Which one of the laws best explains that? That's volume and temperature being proportional or being related. That's Charles's law. Why does the balloon's volume decrease? Because as the molecules cool from the liquid nitrogen, they move more slowly and they hit the walls of the balloon with less force. Therefore, they occupy less space and the volume decreases. Do gas molecules move faster or slower? Obviously, they move slower when the temperature drops. How is the speed of an air molecule related to the pressure it transmits to the inside of the balloon? Speed is proportional to kinetic energy, which is proportional to force. So the lower the speed means less force is imparted to the balloon, and vice versa. The higher the speed, the higher the temperature, the higher the speed, the more force the pressure goes up. This problem was an ideal gas law problem. A healthy adult exhales about 500 mils of gas mixture with each breath. how many molecules are in the typical breath, which is being exhaled at 37 degrees C, body temperature and 1.1 atmospheres. You had to convert 37 degrees C to Kelvin, so it's 310. You had to convert 500 mils to liters by dividing by 1,000, so here's that. Here's the ideal gas law. You're solving for moles because numbers of molecules is essentially moles, so you calculate N, and you plug in PV divided by RT, and I wanted to see all the units because you can see how they all cancel out properly. Liters and atmosphere cancel. Kelvin cancels. You're left with mole units, which is in the denominator of a denominator, so it's really in the numerator. The unit conversion works out. You get 0.022 moles, 2 sig figs, and therefore you multiply that by this number, Avogadro's number, you get 1.3 to the 22nd molecules. Actually, this number only has 1 sig fig, so if you called it 0.02 moles and then rounded this to 1 times 10 to the 22nd, that was fine. I accepted 1 times 10 to the 22nd molecules or 1.3 times 10 to the 22nd molecules as being correct. Number 11, another ideal gas law problem, pretty much the same sort of problem. I'm asking for how many moles of nitrogen are in an airbag given some conditions. You have 35 mils of gas exerting a pressure of 850. Notice the pressure of the airbag is higher than atmospheric pressure. That's the only way the airbag is going to work. It's got to have a pressure higher than what you're experiencing, so it supports your weight. So that has to be converted to atmospheres. 850 mils of mercury is 1.12 atmospheres, or 1.1 is okay since these really only have 2 sig figs. So you plug that in here and multiply by PV. Make sure the units are liters and atmospheres divided by the usual value of R. And 25 degrees C is 298 Kelvin, so you get 1.6 moles. And then multiply that by the molar mass of nitrogen. A lot of people miss this for some reason. Nitrogen is N2, it's diatomic, so the molar mass is twice 14, or just a little bit over 28. So 1.6 times 28 grams per mole. Notice how the units work. You're left with 45 grams. This was just a question about Dalton's law of partial pressures. Air in the lungs is about 13.2% oxygen. If the atmospheric pressure on the top of Mount Everest, which is really high, is very low, that's why it's hard to breathe on the top of a mountain. The air pressure is very low, therefore the amount of oxygen is really low. What's the partial pressure of oxygen in the lungs at this altitude? Well, you just take the percent of this number, that's oxygen, so convert that to a percent. 0.132 times 265 gives you 35 millimeters of mercury. That's such a low number, you can't really survive on that low pressure, so you need air tanks to breathe. Most mountaineers do, unless they're superhuman. The last question in this homework assignment was asking about intermolecular forces. We only really discussed 3 major ones, well, 4: ion dipole, dispersion, dipole-dipole, and hydrogen bonding. I wanted to just ask you about which one of these 3 major ones is the dominant force present in these samples. Carbon tetrachloride is just a nonpolar liquid. It's a tetrahedral molecule, so it's nonpolar. That's just dispersion forces. There's no hydrogen there for hydrogen bonding. This one has a hydrogen bonded to nitrogen, so therefore this has the ability to hydrogen bond to itself. It's a polar gas at room temperature. It can hydrogen bond to itself. That's the major force. Naphthalene is like carbon tetrachloride. It's a nonpolar molecule. It doesn't matter if it's a solid. The only major force in these nonpolar things is a dispersion force caused by the movement of electrons. Ozone is a bent molecule, so it's polar. So dipole-dipole forces are the major intermolecular force holding ozone molecules together. And the last question was, which one of the following compounds has the highest boiling point? Well, really all you had to do is look at the physical states. That's a liquid, a gas, a solid, and a gas. Gases have long ago boiled, and a liquid hasn't boiled yet. Well, it could, but it's going to boil before the solid will. So a solid first has to melt, and then it can boil. So this solid compound has the highest boiling point simply because it is a solid at room temperature. So I'll do the same thing for the rest of the homework assignments for the semester. I just put the latest homework number 7 on Canvas tonight. I'm sure you saw the email, so that will be due next week, and I will review that with you in a future video.